Let's tackle about the brief history of the hydroelectric power plant. In 1827, Binuit Ferneron developed a turbine that are capable of producing around 6 horsepower. Binuit is a French engineer who developed the earliest version of the Ferneron reaction turbine. Ferneron turbine has a 6 horsepower or 4.5 kilowatt turbine that is used 2 sets of blade curved in opposite directions to get as much as possible from the water's motion. By 1837, Ferneron had produced a turbine capable of 2,300 revolutions per minute, 8% efficiency, and 60 horsepower with a wheel a foot in diameter and weighing in only 40 pounds or 18 kilograms. Besides, its more obvious advantage over the water wheel, Ferneron turbine can be installed as horizontal wheel with a vertical shaft. In 1849, James Francis developed the first modern water turbine, which is the Francis turbine. The Francis turbine is a type of water turbine. It is an inward flow reaction turbine that combines radial and action flow concepts. Francis turbines are the most common water turbine in use today and can achieve over 95% efficiency. In 1878, the world's first hydroelectric project was used to power a single lamp. It is developed at Cragside in Northumberland, England by William Armstrong. In 1995, the International Hydropower Association, which is known as IHA, began to work on IHA sustainability guidelines in 2004. International Hydropower Association was founded on 16th of November in 1995. In the quarter of a century since then, the hydropower sector has undergone a momentous change and grown considerably. IHA's mission is to advance sustainable hydropower by building and sharing knowledge on its role in renewable energy system, responsible freshwater management, and climate change solutions. These guidelines led to the development of the Hydropower Sustainability Assessment Protocol or HSAP, a multi-stakeholder tool for assessing projects at all phases of their life cycle. This development led to a fundamental shifts in how best to plan, development, and operate hydro projects and resulted in growing appreciation of the technology's role in combating climate change, reducing poverty, and boosting prosperity. From 2000 to 2017, nearly 500 gigawatt in hydropower installed capacity was added worldwide. It represents an increase of 65% on growth since 2010. Hydroelectric power plant. What is a hydroelectric power plant? It is a facility at which electric energy is produced by hydroelectric generations. It is also called hydro power electricity, which converts the potential energy of falling or fast flowing water into mechanical energy. Because hydropower plants can generate power for the grid immediately, it has essential backup power during major electricity outage or disruptions. Hydropower provides benefits beyond electricity generation by providing flood control, irrigation support, and clean drinking water. Hydropower is affordable. Around 60% of all renewable energies is generated by hydropower. The sector produces around 16% of total electricity generation from all sources. In its 2021 hydropower special market report, the International Energy Agency or IEA reports that hydropower accounts for nearly a third of the world's capacity for flexible electricity and supply and has the potential to provide even more. No country has come close achieving 100% renewables without hydropower in the energy mix. Hydropower installed capacity reaches to 1,330 gigawatts in 2020 as generation hit a record of 4,370 terawatts per hour. China, Brazil, the USA, Canada, and India are the largest hydropower producers by installed capacity. Hydroelectric power plant is a low carbon pollution free plant. Hydropower is among the cleanest source of electricity with a low greenhouse gas emission intensity compared to other energy forms. So, trivia. Did you know that the hydropower utilizes the Earth's water cycle to generate electricity? This is because water generates kinetic energy as it flows downstream. This energy is what is transformed into electricity. Did you know that the pump storage is a type of hydropower that works like a battery? It stores energy by pumping water from a reservoir at a lower position into another reservoir at a higher position. When you need power, you simply release the water, which rotates the turbine and generates electricity as a result. Did you know that some hydropower facilities don't have dams? These facilities are normally so small that they can simply be located near irrigation trenches. Some hydropower plants can simply use a diversion to channel water through a generator. Did you know? A massive volume moving water is needed to generate electricity at a hydropower facility. It is about 18 gallons of water are needed to generate just 1 kilowatt hour of electricity. The advantage and disadvantage of the hydroelectric power plant. The advantage of hydroelectric power plant. First, a hydroelectric power plant is an environment friendly. Hydropower plant does not emit carbon dioxide or does not emit pollution into the atmosphere. Hydropower is a climate-friendly energy source, generating power without producing air pollution or toxic by using products. Using hydropower avoids approximately 200 million metric tons of carbon pollutions. Number 2. Hydropower creates reservoir. Hydropower reservoirs are natural and made to use and store water for future use. A hydroelectric reservoir is a large collection of water behind a hydroelectric dam that make use of potential energy of water for generating electricity. This water is held back by the dam and the small amount is allowed to fall down the base of the dam to generate electricity when it is needed. Number 3. Hydropower is a flexible. Hydropower can be used as an alternative and main source of power. Hydropower can supply electricity or store it to meet real-time energy needs. Hydropower has a high efficiency. As of today, the hydropower efficiency of the hydroelectric power plant is about 90%. Number 5. Hydropower is a low-cost electricity. Once the dam is built and the equipment was installed, the free-flowing water is used as an energy source. Unlike other power plants that uses other resources for their operations. Number 6. Hydropower is a low operating and maintenance cost. It is because their structures are sturdy and their equipment is simple. Other power plant uses complex equipment that has high maintenance cost. Hydroelectric power plant are reliable and durable. That the machineries involved has relatively few moving parts. Because excessive heat is not produced, cycling has the minimal effect on machineries, which contributes to long life and low maintenance. Compared to other electricity sources, hydropower also has relatively low cost throughout the duration of the full project lifetime in terms of maintenance, operations, and fuel. The disadvantage of the hydroelectric power plant. First, the hydroelectric power plant has high initial cost. It is because the equipment should be ready, the power line should be ready, and also the construction materials of the building dams is expensive. The initial cost of the hydroelectric power plant is very high due to dam structure and other essentials. Because hydroelectric power plants has fewer moving equipment, a rigid structure, then the operating and maintenance costs are reduced. Number 2. Disruptive to aquatic life. This is due to building dams that holds the water from the reservoir and its high pressure water discharge. Dams disrupts the ecosystem within and around rivers, reduce biodiversity, and mess with the water quality. Number 3. Low power generation in summer. It is due to temperature fluctuations and drought that consequently affect the hydropower generation. Number 4. Hydropower is affected by weather. These are the weathers that affects the hydroelectric power plant. Temperature fluctuation, rainfall patterns, floods, and droughts are all major signs of climate change that have strong effects on river system, which allows consequently affect the hydropower generation. As example, when there is an incoming typhoon, there are tendencies that the water will rise above the maximum capacity of a dam. In the assurance that this will not happen, they will release a certain amount of water preventing it to overcome its limitations. Number 5, last, the limited reservoirs. Due to limited reservoirs, we cannot simply build dams anywhere we please, and those places that are applicable for this have been used for this purpose.
A hydraulic electric plant consists of a reservoir for storage of water, a diversion dam, an intake structure for controlling and regulating the flow of water, and the conduit system. The height to which the dam may be built is usually limited by the extent of flowage damage. Our next topic is all about the 13 elements of the hydroelectric plants. Element number 1, storage reservoir. It is a fundamental requirement of a hydroelectric plant. It uses to store water during surplus flow periods and provide it during lean flow periods. Therefore, assisting in the supply of water to the turbine is based on the demand on the power plant. Element number 2, dam. The dam's function is not only to raise the stream's water surface to create an artificial head, but also to provide pondage, storage, or diversion into conduits. A dam is the most expensive and crucial component of a hydro project. Dams are made of concrete or stone masonry, as well as dirt or rock fill. Masonry dams are classified into 3 types: solid gravity, buttress, and arc dams. Solid gravity is composed of concrete and may be used in a variety of locations. The dam's height, which cannot be extremely high, is determined by the strength of the subsurface layers. Arc dam is a curving dam that uses arc action to convey a large percentage of its water pressure horizontally to the abutments. Buttress dam. The buttress or deck dam has a slanted upstream face which exerts a considerable downward force that offers stability against overturning or sliding. This type of dam is better suited for poor foundations and earthquake-prone areas. Element number 3, pore. The pore serves as a regulating reservoir, storing water temporarily during light load period and providing the same for initial increase on account of increasing load, during which water in the canal is being accelerated. Element number 4 is spillway. This is constructed to act as a safety valve. It discharges the overflow water to the downstream side when the reservoir is full, a condition mainly arising during flood periods. Element number 5. The intake includes the building at the intake of conduits, tunnels, or plumes, known as headworks. This structure includes booms, screens, or garbage racks, and sluices that divert and prevent debris and ice from entering the turbines. Element number 6, surge tank. This storage reservoir, called the surge tank, is usually located as close to the power station as possible, preferably on ground to reduce the height of the tower. Element number 7, penstock. It is built of steel or reinforced concrete. Steel penstock are almost always welded on the longitudinal seam. Element number 8, valves and gates. Gates at the entrance on the turbine casing are usually all that is required in low head plants to shut off the flow and provide for unwatering the turbine for inspection and repairs. Individual host-operated gates are offered in circumstances when frequent shutdowns are required and inspection time is restricted. Element number 9, trash racks. These are designed to keep floating and the other debris out of the turbine. In other circumstances, when large diameter turbines are used, the racks are eliminated, but skimmer walls or booms are normally provided to prevent ice and other material from entering the unit. Element number 10, trail race. After doing its useful work in the turbine, the water is discharged to the trail race, which may lead to the same or another stream. The trail race should be designed and sized so that water can exit freely and the jet of water can travel freely after leaving the turbine. Element number 11, drop tubes. An airtight pipe of suitable diameter attached to the runner outlet and conducting water down from the wheel and discharging it under the surface of the water in the trail race is known as drop tube. Element number 12, prime movers or water turbines. In hydroelectric power plants, water turbines are used as prime movers and their function is to convert the kinetic energy of water into mechanical energy, which is further utilized to drive the alternators, generating electrical energy. Element number 13, powerhouse. The powerhouse is a structure that protects hydraulic and electrical equipment. In most cases, the entire equipment is supported by the powerhouse's foundation or substructure. Next topic is principles and operations. Generally, hydroelectric plants are in hilly areas where dams can be built easily and large water reservoir can be made. In a hydropower plant, a waterhead is created by building a dam across a river or lake. The water turbine changes the kinetic energy of the falling water into mechanical energy at the turbine shaft. In simple words, falling water spins the water turbine. The turbine drives the alternator coupled with it and converts mechanical energy into an electrical energy. There are three types of hydroelectric: the availability of head, quantity of water, and nature of load. In availability of head, we have low 20 meter, medium 300 meter, high greater than 300 meter. In quantity of water, we have run-off river plant without pondage, run-off river plant with pondage, storage type, pump storage, and mini and micro hydro plant. Lastly, in nature of load, we have base load and peak load.
Good morning, everyone. Now, as we finish to discuss our lecture part of the hydroelectric power plant, we will now go through its mathematical approach. As we all know, when we have the mathematical approach, we have the following mathematical formulas to solve any given problems. So first, we have our power with the formula of specific weight times discharge times height or the head elevation times efficiencies. It's either to be efficiency mechanical, electrical, or in generator. Some equations are derived as follows. P is equal to efficiency P G H Q multiplied all in all. Our P is a power output measured in watts, efficiency of our turbines, rho as our density. Sometimes it is taken as our specific weight of the fluid, particularly water, as in other formula or conversions. We also have the G as the acceleration of gravity and the height expressed in length, meters or in feet. Depends upon metric or in English. Next, we have the discharge. Q is equal to A times B, whereas Q is a discharge or the flow rate, A as the cross-section area of the channel, and V as our velocity. Proceeding, we have also the specific speed of a multi-jet machine, whereas N sub SMJ is equal to square root of N times N sub SS1, whereas our NSMJ is the specific speed of a multi-jet machine, N is a number of jets, and N sub SS1 is a specific speed for a single jet machine. Next, tangential plate and the bucket speed. The formula is V is equal to angular velocity of our fluid, the R as a radius, and can be equated also as pi times d times n over 60. Next equation is the velocity of jet from the nozzle. Velocity is equal to coefficient of velocity ranging for 0.997 to 0.99 times 2 times g as the specific gravity times h skewed to 1/2 raise. Next is the energy transferred to the wheel. Energy is equal to pressure 1 minus pressure 2 over rho g, where plus velocity initial squared minus velocity final squared over 2g. We also have the hydraulic efficiency. Hydraulic efficiency is equivalent to E over H, or equal to V sub W1 times V sub B1 over GH. Next formula is the overall efficiency. Overall efficiency can be equal to P, or the total power output, over rho times Q, or the discharge, the G as a gravity, and our H. Next formula is Q is equal to A times CV, our coefficient velocity, times 2 times G times H raised to 1/2 with the quantity unit of cubic meter per second. Next is our NS, which is equal to N times P raised to 1/2 over H raised to 5 over 4. Take note also that we have in formula Q, we also can have the turbine speed factor, which is equivalent to turbine speed factor equals pi times D times N over square root of 2G. So now we will going to solve a 5 problems specifying different solutions and different use of our equations. Sample problem number 1. 45 kilowatt of the shaft power is developed by a turbine working under an available head of 40 meters. The energy transferred from the water to the runner is 350 joule. Assuming a mechanical efficiency of 95%, what is the discharge through the turbine in cubic meter per second? We have a given of the following: shaft power of 45 kilowatt, head of 40 meter, mechanical efficiency of 95%, and hydraulic efficiency of 87%, assuming we have it's in a given shaft power. Now, our required is a discharge. So, our equation to be used is shaft power is equal to specific weight of water, discharge, times head times mechanical efficiency times hydraulic efficiency. Given the values, we will plug in all the data. So we have 45 kilowatt is equal to 9.81 meter cube per second times Q times 40 meter times 0.95 times 0.87. Calculating, we have the discharge of 0.135 cubic meter per second. Sample problem number 2. A vertical draft tube is installed on a Francis turbine, and the total head to the center of the spiral casing at the inlet is 38 meters, and velocity of water at the inlet is 5 meter per second. The discharge is 2.1 cubic meter per second. The hydraulic efficiency is 0.87 and overall efficiency is 0.84. The velocities at the inlet and exit of the draft tube are 5 meter per second and 1.5 meter per second respectively. The top of the draft tube is 1 meter below the center line of the spiral casing, while the tail rails level is 3 meter from the top of the draft tube. There is no velocity of whirl at either top or bottom of draft tube, and leakage losses are negligible. So what is the power output of the turbine in kilowatt hour? Our given are as follows. Pressure head is equal to 38 meters. Initial velocity of 5 meter per second. Final velocity of 1.5 meter per second. Discharge of 2.1 meter per second. Hydraulic efficiency of 0.87. Total efficiency of 0.84. And with elevation head of 1 meter plus 3 meter as given on the problem. We are going to find the turbine output. So, our formula is turbine output is equal to specific gravity of water times discharge times the height times efficiency. As we can notice, we don't have any given on height. So we were going to solve for our H. H is equal to pressure over specific gravity plus elevation plus V sub A squared minus B sub B squared over 2G. Plotting all the values, we have 38 meter as a pressure head plus 1 plus 3 meter as our elevation plus 5 raised to 2 minus 1.5 raised to 2 all over 2 times 9.81 meter per second squared. Calculating, we have the H as 43.16 meters. Now, we will substitute our value to get the turbine output. Turbine output would be equal to 9.81 as our specific weight of water times 2.1 times 43.16 meter as our H on the previous answer and our efficiency of 0.84. Calculating, we have our turbine output of 746.9 kilowatt. Sample problem number 3. A hydroelectric generating station is supplied from a reservoir of capacity 6 million cubic meter at a head of 170 meters. Assume hydraulic efficiency of 80% and electrical efficiency of 90%. The fall in the reservoir level after a load of 15 megawatts has been supplied for 3 hours. If the area of the reservoir is 2.5 kilometers squared, what is the closest answer? Our problem states the following given. The capacity of 6 million cubic meter, head of 170 meters, hydraulic efficiency of 80%, electrical efficiency of 90%, power of 15 megawatts, supplied hour of 3 hours, and the area of 2.5 kilometers squared. We will going to find our height, and our formula for the height is volume is equal to area times height. But before we got our height, we will need first to get our volume. To get the volume, we will now use the power equation, which is power is equal to specific weight of water times the discharge times the head times electrical efficiency times hydraulic efficiency. With those values, we will now form our equation as 15,000 of power is equal to 9.81 times Q times 170 meters times 0.80 times 0.90. Calculating, we have our discharge of 12.492 cubic meter per second. As in condition, in 3 hours, our volume of water consumed would be volume is equal to our discharge 12.492 cubic meter per second times 3 hours converted to 3,600 seconds. Our volume now is 134,914 cubic meters. Then, we will equate now the volume, area, and height. V is equal to AH 134,914 cubic meter is equal to 2.5 times 10 raised to 6 meter squared times the height. Thus, our height is equal to 5.39 cm. Sample problem number 4. In Maria Cristina Hydroelectric Project, the available head is 140 meters. The water flow is 1 cubic meter per second. Efficiency of the turbine is 95%. Efficiency of the generator is 95%. It is 3-phase, 60 cycles. Voltage delivered is 4,160 volts. And now, determine the estimated yearly income of the plant if cost of the generated electric energy is 0.60 centavos per kilowatt hour. From the problem, we have the following given. Head of 140 meters, discharge of 1 cubic meter per second, turbine efficiency of 95%, generator efficiency of 95% also, and the cost of 0.60 centavos per kilowatt hour. We're going to find the yearly income. Now, we will have first the yearly generator output answer. Our formula for this is specific weight of water times the discharge times the turbine efficiency times the generator efficiency times a constant of 8,760. Plotting all the values of 9.81 kilonewton per meter squared times 1 cubic meter per second times 140 meters times 0.95 times 0.95 times 8,760, we will calculate a 10,857,963 kilowatt hour. Now, we will substitute from the original equation of yearly income is equal to yearly generator output times 0.60. As being equated, our yearly income will become 10,857,963 kilowatt hour times 0.60, garnering a yearly income of 6,514,777.80 centavos. Sample problem number 5. A hydroelectric plant discharges water at the rate of 0.75 cubic meter per second and enters a turbine at 0.35 meter per second with a pressure of 275 kilopascal. Runner inside diameter is 550 millimeter. Speed is 520 rpm and the turbine efficiency is 88%. Find the turbine speed factor. From the problem, we have the following given. The discharge is equal to 0.75 cubic meter per second, velocity of 0.35 meter per second, pressure of 275 kilopascal, diameter of 550 millimeter, which is equivalent also to 0.55 meter. N is equal to 520 RPM, and the efficiency of 88%. We're going to find the turbine speed factor. Our formula of turbine speed factor is turbine speed factor is equal to pi diameter times N over square root of 2 GH. As we notice, we don't have H, so we will first calculate the hour H before proceeding to the next equation. Solving for H is equal to pressure over specific weight of water plus V squared over 2G. Plotting the values, we have 275 kPa over 9.81 kilonewton per meter squared plus 0.35 squared for velocity over 2 times 9.81 meter per second squared, calculating a 28.039 meters as our H. Then now, we will substitute our values. Turbine speed factor is equal to pi times 0.55 times 520 divided by 60 all over square root of 2 times 9.81 meter per second squared times our H 28.039 meters. Thus, we will have our turbine speed factor of 0.638. Moreover, our discussion will not be complete if we don't have the future and the present representation and conditions of our hydroelectric power plants. We are going to show a video on what is the progress of hydroelectric power plant in the present times.